Welcome to all of you. Now we discuss practical problem 16, Newton's backward interpolation by C programming. The problem 16, Newton's backward interpolation, write a C program to compute the value of fx at 1.40 plus r plus 1 by 100 by suitable interpolation formula from the following table. This is the x, fx, the x, fx, and the R is the last digit of your C roll number. Is the programming the variable double variable x 20 y20 d 2020 sum xn xx h v and term and integer variable n m I j and r. Printf enter the value of r. This is the last digit of your C roll number, and the interpolating points xi, that is x0 to x9. There are 10 interpolating points, this 0.20 up to 1.55, and the corresponding value of fx, that is yi, is y0 to y9, and the value of x for which interpolation is required is x called xx is 1.40 plus r plus 1 by 100. We use here Newton's backward interpolation because these the interpolating points are equispaced. The difference step length is this 0.15, and this point 1.40 plus r plus 1 by 100, this 1.40 uh, lies in the end of the table. So this is the we use here Newton's backward interpolation here. Here in the total number of interpolating points, this 10, and n minus 1 is the subintervals, total number of subintervals n minus 1. So this is the this 9 plus 1, this is the interpolating polynomial, Newton's backward interpolating polynomial, this px, and this is the n plus 1 interpolating polynomials x0 x1 x2 xn, and corresponding y0 y1 y2 yn, and the values of fxi at these nodes, this, but the actual uh, explicit expression of this fx is unknown here. This is the first order difference, second order difference, third order difference, fourth order difference, and fifth order difference, and so on. Here this we use this delta y0 from the backward, this delta 2 y3, delta 2 delta 3 y2, delta 4 y1, delta 5 y0 in the formula of Newton's backward interpolation formula. This yn plus this is the yn, actually this is the yn, and this is the yn, this yn v by factorial 1 delta yn minus 1, actually this is the delta yn minus 1, and v is the x minus xn by h. V is the phase dimensionless quantity, and this v values of v lies between -1 to 0 to minimize the error, and v plus v into v plus 1 by factorial 2 delta 2 y n minus 2, that is delta 2 delta 2 3 y, and so on so on. So for y, here we actually example this 5 plus 1 interpolating points here, but in the given example, so 9 plus 1 interpolating points, so this is the y9, and this delta y8 and delta 2 y7 and delta 3 y6 and delta 4 y5 and delta 5 y5, and so on. And this is the formula, this, and px is the interpolating polynomial, the is of degree at most n. Here this is the 9 because there are n plus 9 plus 1 interpolating points x0 to x9. So degree of px in the given problem at most degree 9. And this is the h, the stable length xn minus x0 by h, x minus x by n. Here, this is the xn. Xn is uh, the end value of the x, the end value of x, because xn, that is x9. Here x9 is this, x9 is this 1.55, because this x is this 1.40. So xn is the end point of x. This is the ending value of x, that's xn, and h is the stable length. And for I equal to 0, I less than equal to n, I plus plus, here di0, that is equal to yi. So values of yi, I equal to 0 to n for 9, 0, 1, 2, 3, 4, 9, and this gives the value of all y0, y1, y2, and d00 is the y1, y0, d10 gives the y1, and this is the d50, y5, and so on. D90 is the y9. And for j equal to 1, j less than equal to n, j plus plus, and j is the order of the difference, and this delta j actually. So j1 represents the first order difference, this I equal to 0. So I equal to 0, d01. D01 is the actually d01 is the first order difference, this g01 is the delta y0, and so on. So when j equal to 1, the first order difference, and I runs from 0 to n minus 1, that is 8. So we get this uh, first order difference, this delta y0 to up to delta y8, when j equal to 1. And for j equal to 2, this I equal to 0 to 9 minus 2, that is 7. So I equal to 0 to 7 when j equal to 2, and the second order difference, so this column, the second order difference delta 2 yi, actually this is the delta 2 y0 to up to delta 2 y7. And the print the difference table, this I equal to 0 and j equal to 0 to n minus I, this percentage 15.1 to lf. Lf is the floating representation, double is the double variable double type. So here we use the floating type representation lf dij. Actually we write here row wise, this we write here row wise differentiation, delta y0, delta 2 y0, delta 3 y0, delta 4 y0, delta 5 y0, and this and so on. Or j equal to 0 to up to n minus I, that is equal to 9 minus 0 for I equal to 0. So for I equal to 0, so j equal to 0 to 9 is the um, first row for difference delta 0, delta y0, delta 2 y0, delta 3 y0, and for this value. And next print / and new line, and j equal to 1 for the second row, and this. Enter the column number in which the noise level appears, otherwise press 0. Scan M, enter M, value where the noise level appears, this at this point. Put this, what is the noise level? Already we discussed the previous lecture. This noise level is the successive difference gradually decrease in significant figures, and owing to propagation of errors, the errors gradually increase in the successive differences. Hence, a stage is often reached at which the computed differences are of same order as their errors, so that these differences are thoroughly unreliable and useless. And this stage is called noise level. To avoid this, we must this difference table. The computation of difference should be stopped just before one gets differences having only one significant figure, and one figure differences and differences further on should not be used in the computation. A difference table has to be stopped just before the differences become irregular. So this is the noise level, and this m equal to n. If there is no noise level, so put 0. Then value of m equal to n, that is n equal to 9. Else m is equal to m minus 2. And this is the m, p is the phase, that is the x minus xn by h, and p is the phase, this is the x minus xn by h. Sum yn term v, and for j equal to 1, j less than equal to m, j plus plus sum equal to sum plus term into d n minus j into j. So from this formula we get this sum yn, actually yn, this sum equal to new sum equal to previous sum, that is yn, plus term equal to v into d n minus j in equal to 9, 9 minus 1, 8, d8 1, d8 1, actually d8 1 means this point. So this yn plus this d delta y8, this is the v by factorial 1 into delta 8. So this term is v, so v into delta y8. And the term equal to term v plus j divided by j plus 1. So previous term, this previous term, new term equal to previous term. Previous term is v into v plus 1. So new term is this, v into v plus 1 by factorial 2 delta to y7, delta to y7, because n equal to 9. So this v into v plus 1 by 2 by 2, this v into v plus 1, this term. And for j equal to 2, this is the new sum equal to previous sum, and previous sum is the v, and the v plus v by factorial 1 and delta y8, previous sum, and plus term, this the term is this, this the term is this v into v plus 1 by factorial 2, and this d n minus j in 9 minus 2, that is 7, 7 j equal to 2. So delta 2 y7, actually delta 2 y7. So this term is this, so this delta 2 y n equal to 9, so delta 2 y7, and so on. So ultimately we get this print y percentage 6.4 lf equal to percentage 15.1212 lf, this xx, and sum is this return 0. Let's save this problem, compile, no errors here, and compile and run again. And this is the Newton's backward interpolation. Enter the value of this, put here 5, then enter the value of r. This is the difference, this is the y0, y1, y2, this is the first column, gives the fxi, and the second column delta, first order difference, delta y, delta 2y, delta 3y, delta 4y, delta 5y, delta 6y, delta 7y, delta 8y, delta 9y. And in this table, for this column, this is the significant figure 2 2, and this is the minus 90. So there is some irregularity this. So at this column 1 2 3 4 5 6 7 8. So enter the column number in which the noise level appears, otherwise press 0. Here the column number 8, put here 8, where the noise level 1 2 3 4 5 6 7 8. So there are some noise, there is some noise, so put here the column number 8 and enter this. This is the value of y at the point 1.46, for r equal to 5, we get 1.750693041861 is the required answer, the required functional value of this. Thank you for watching this video.